I'm definitely mic'd. Hey everyone, how's it going? That was kind of weak. Don't make me feel too much like a camp counselor up here. How's it going? Excellent. I hope everyone had a good weekend. Welcome back. Today is Monday, of course. Alex is still in England, so I'm giving his lecture on Monday. He should be back for Wednesday to give you guys the next lecture. It's not quite 3:10, so I won't launch into this just yet. Did anyone think of any jokes over the weekend? We didn't have any jokes on Friday. No, nary a joke to be found. It's a shame. You guys are cheating yourselves with that, really. All right, so let's get started. So today's lecture is going to be a bit different from what we talked about last week. Last week we talked about different techniques that astronomers use when they spread out the different wavelengths of light that come from astronomical objects and how we can determine things such as the object's chemical composition, their radial motion, their temperature. This week we're not going to talk about the light as much, but we're going to talk instead about the tools that astronomers use to collect the light, the so-called tools of the trade. And of course, when we talk about tools of the trade, referring to astronomy, we're referring to the telescopes that astronomers use. And so, how many people, by a show of hands, how many people have been to a star party so far? All right, maybe a little more than half of you. That's really good. Those of you who have not yet been to a star party, you really ought to go. It is a fantastic experience. And if you have gone, then you've already come in contact. You've had experience with one telescope, the 14-inch telescope on the rooftop of Campbell Hall. So you sort of know a little bit about what it's like to look through that. I'm going to talk about a couple different kinds of telescopes today. And you'll get to see some pictures of some of the world's biggest and best telescopes that are used at the cutting edge of astronomical research. All right, so first of all, a couple of announcements pertaining to what's on tap this week. Again, your next opportunities, if you haven't yet been to a star party, are going to be Tuesday and Thursday this week from 8:30 to 9 o'clock, from 8:30, to 9:30 p.m. Come to the roof of Campbell Hall and see some objects. This early in this fall, we're going to be mostly featuring Jupiter. And so if you look through the telescope, you can see Jupiter very clearly. You can see the 4 Galilean moons. And it really is a fascinating sight. I'm kind of jaded as a graduate student astronomer. I've seen things through a telescope many, many times. But every time I look at Jupiter and its moons through our telescope, it still makes me say, wow, the first time all over again. So go ahead and definitely take a look at that. We've got some other cool stuff we can show you too. And then also, just like last week, we have the second homework assignment is due Friday at 5:15 in the basement of Campbell Hall. Another announcement, which is pertinent to next week, is that there's going to be an in-class quiz in your discussion sections, I should say, not in here, next week in your section. It's going to take about half the section. It'll be about 20 minutes, and it can cover material that includes the lecture before your section. So let me give an example, because how much material you're responsible for will depend on what day of the week you have section. So for instance, if you have section on Tuesday, then the lecture right before your section would be Alex's lecture on Monday next week. And you're not responsible for that lecture's material for a Tuesday section. You would instead be responsible through the lectures Friday this week. So if anyone has questions about what they need to know for the quiz, you should email your GSI or come talk to me. And this quiz is graded. It goes towards your overall course grade, so you guys should have been showing up to section anyway, but you especially need to show up next week to take the graded quiz. Okay, let's get into telescopes. So why anyway do astronomers build telescopes? Is it just that we like taking the government's money and spending it by the millions of dollars? I mean, I get a kick out of that, but there is more to it. The primary reason that we use telescopes instead of just our naked eyes to do astronomy is that we want to see really faint objects. We need something that is effective at collecting a lot of light, because these distant faint objects don't give us all that much to begin with. And so when we talk about light collection, what we really want to talk about is the area of the telescope. So to make a comparison, you can compare how much light a large telescope collects versus how much light you collect just looking at the night sky with your naked eye. And so when we're talking about the area, we'll use the area of a circle. Most large telescopes have circular mirrors or circular lenses. The pupil of your eye is roughly circular. And so this is a good shape to think about. So the diameter of that circle for a large telescope, Alex has put up the figure 6 meters for the diameter of a large telescope. And I don't know specifically of any 6-meter telescope. Most of the world-class telescopes these days are in the range of 5 to 10 meters. 6 meters is going to make the math work out nicely. It certainly is a reasonable value for the size of that telescope. And so, by the way, 6 meters is about 20 feet. So 20 feet across, that's already a pretty big object we're talking about. Whereas if you compare, the pupil of your eye is actually only about a millimeter across. I think I'm even doing it bigger than it actually is. So the pupil of your eye versus a large telescope, because there's 1,000 millimeters in every meter, you have a ratio of diameters of 1,000. But when we want to compare how much light you can actually collect, we're not talking about the diameter as much as we're talking about the area. And so to get the actual ratio of light collecting ability, or how faint an object you can see, then you want to apply the formula to go from diameter to area. And so the area of a circle is pi times the radius squared. The radius is the diameter divided by 2, and so if we plug in this d over 2, we get pi d squared divided by 4. Now, the good thing is that in this case, you don't even have to remember the pi divided by 4 part. That's completely irrelevant because pi and 4 are constants. What you simply need to know is that diameter, a unit that gets measured, a quantity that gets measured in units of meters, a distance quantity, goes like the square root of area, which is a square meter quantity. And probably a more clear way for me to say that is that area goes like diameter squared. So when I'm comparing the ratio of the areas, the area of a large telescope divided by the area of your pupil, that ratio is simply going to give me the ratio of the diameters then squared. And since we know that diameters have a ratio of 1,000, when we square 1,000, we get 10 to the 6 equals 1,000,000. And so a telescope can see something 1,000,000 times fainter than your eyes, a 6-meter telescope to be specific. Clearly, if you're in astronomy, it's advantageous to be able to see faint objects that are very far away. I'm sure you guys are aware that you can see far less with your naked eye, even in a very clear night, than something like the Hubble Space Telescope or the Keck Telescope or any of these large telescopes can actually see. So here's a picture of a ground-based telescope. This is the dome of the 200-inch Hale Telescope in Palomar Observatory. It's in the mountains between LA and San Diego. This is a telescope that Alex would have used as a graduate student. It's owned by Caltech, where he went to graduate school. And at least at the time Alex was a graduate student, this was definitely one of the best telescopes in the world. So that was the dome rotating. Here's the inside, and hopefully you can see just by the scale of this thing, this telescope, compared to everyday objects, this is absolutely a mammoth thing we have here. Telescopes, large telescopes, are completely enormous. And so this thing in the foreground, this is simply the strut that supports the telescope and maneuvers it to point it at different parts in the sky. The telescope itself is this structure right here. You can see this would be the primary mirror. So when we say it's a 200-inch telescope, it means that this mirror is 200 inches across in diameter. Again, that's about 5 meters. There's a secondary mirror up here. We'll talk about later in this lecture how astronomers use multiple mirrors to reflect the light in the direction they want to. And if you were using an instrument like a spectrometer or something else to analyze the light, these instruments would get stuck behind the mirror and the light would eventually find their way into that instrument. And so again, I want to emphasize just how enormous this thing is. I know the final exam for this class, not to freak you guys out by talking about it already, but it simply is located in the basketball stadium in Haas Pavilion. And if you guys have ever been, who here has been inside Haas Pavilion yet? Okay, a lot of you. So this building, this dome that encloses the Hale Telescope, is almost certainly bigger than Haas Pavilion. We are talking really large buildings here. And again, this stepladder, if you've been to a star party on the roof of Campbell Hall, we know we have a stepladder in there. This is certainly bigger than that stepladder. You could imagine yourself maybe climbing up this stepladder and just being dwarfed by the instrument that you're using to collect this light from distant objects in the heavens. There's another advantage, though, to having a big telescope besides the fact that they can collect lots of light. And that has to do with the resolution or the sharpness of an image that you get. And the relationship between telescope size and resolution is that the bigger a telescope you have, the smaller you can see your details when you actually take an image of the object. And this is a little bit misleading, especially because when people look for amateur telescopes, they tend to think about things in terms of magnification. What's the magnification of this telescope? How much is this magnified? That's really rather a misleading figure. And when astronomers think about telescopes, they don't heed the magnification so much. It turns out not to be that relevant in terms of how good an image you can get. What we really are concerned about is the resolution. And when I said that small things are better, what I mean is that if you have a lot of details, but they're not resolved well, so they get blurred over a large area instead of a small, sharp area, then they're going to blend together. And you'll get to the situation where you can't really tell different features of the object you're trying to look at apart. And we'll definitely look at some images in this lecture that show poor resolution, where you can't see things very sharply, versus good resolution, where you can see lots of the little tiny details that make these images so spectacular. So we want to be able to see small details, and actually having a big telescope helps that. There's a detail with the atmosphere that I'll get to in just a sec. But here's an example. So on the left here, these two panes, one of them is in blue light, one's in red light. These show what it would look like if you were looking at a binary star system through a pair of binoculars. Then in the middle, we have if you were looking at the same system through a small telescope, and at the end, the same system through a larger telescope. And so I hope hopefully you guys can clearly see as we go from the binoculars to the small telescope to the large telescope, in both images, these guys get smaller, meaning that you have better resolution. And so, again, you want to be seeing things that are nice and crisp, like this image on the right you can get from a large telescope, versus over here or here where they're kind of blurry, or you see in the red through the binoculars, you can barely tell that this is two separate objects. And it wouldn't be good if you were trying to do research on this object and you didn't even know how many things you were looking at. So here we have poor resolution where you can only distinguish really one object to really good resolution with a larger telescope. There is, however, one disadvantage to this, or one thing that confounds astronomers when we try to use larger telescopes to get good resolution, and that is that the Earth's atmosphere is constantly working against us. As light comes from objects in outer space and reaches the ground where most of our telescopes are, it has to travel through the Earth's atmosphere. And it so happens that the atmosphere actually bends the path of that light and jiggles it around. I did a lot of stuff with jiggly motions on Friday. This is a different concept. But basically, the atmosphere is a turbulent thing, and it's moving around where exactly individual paths of light land on the ground. And this tends to blur out images and distort them. And it actually happens that making yourself a bigger telescope after a certain extent doesn't do anything to fix this at all. If you can't correct the atmosphere, there really is no point to try to build a bigger telescope to get good resolution. It's going to defeat you. The size at which the atmosphere defeats you is about a 10 to 20 centimeter telescope, so about half a foot. So if you have anything bigger than maybe a half a foot telescope and you don't have some way to correct for what the atmosphere is doing, then you're looking at as sharp an image as you're ever going to get from the ground. No matter how much bigger you make your telescope, the image isn't going to get any sharper because the atmosphere will mess it up. However, large telescopes always do have the advantage of having a large collecting area. So if you made your telescope bigger, you'd be able to see fainter things, but they wouldn't look any sharper. So, and here's an example of what atmosphere does to a star. So this is, I think, a very short exposure of a star taken through a telescope with the atmosphere interfering. And so what we would like to see would be a very sharp, precise point from the star, something more like one of these guys. But instead, because the atmosphere is throwing around the light from the star as it comes to the Earth, you can see it actually moves some of it over here, and it moves some over here, and some over here. And even in this short exposure, you can see that we're not seeing really a clear image. And if you exposed for even longer, if you let light collect in your telescope, basically the atmosphere would throw the light around and you just sort of get a big, bright blur eventually that took up this entire area. So instead of a sharp image, you'd basically get a blur that wouldn't be very appealing to you. So any questions about why we want large telescopes or what the atmosphere does to them? All right, no questions yet. So let's talk about the different kinds of telescopes astronomers use and what these telescopes actually employ to collect the light where we want it. So the first kind of telescope, the oldest kind we're going to talk about, is a refractive telescope, a refracting telescope which uses glass lenses to get the light into the eyepiece. As the slide said, they were invented in Holland around 1600. Galileo used this telescope, but he didn't invent it. And so what happens is, just like a prism, a glass prism, when you send light through a glass lens, it's going to bend that light. And in this case, we have incoming parallel light rays. They hit the glass lens, and they get bent towards a focal point. And your goal when you're trying to make a sharp image is to collect all the light at some focal point right here. And so a common example of a small refracting telescope, if anyone does own a pair of binoculars, what a pair of binoculars really is just a pair of two small refracting telescopes. So each monocular in that pair is going to be a refracting telescope right there and right there. And maybe it was a little bit confusing when I said that these light rays come in parallel, why I specifically draw it like this. And that has to do in astronomy with the distance to these sources. As a contrary example, if someone in the back of the room held up like a light that I was trying to see through a telescope and I had a large glass lens to try to see that light, well, the light hitting the left end of the lens would go back to the person at a certain angle. the light that was coming into the right end of the lens would trace back to the person at a different angle, and you wouldn't really have parallel light coming into my telescope. It would be coming at an angle. However, astronomy, things we look at in astronomy are so distant that essentially they're distance off almost at infinity. We say virtually at infinity for these telescopes make the light rays parabolic. So in this diagram, you can see something kind of far from the Earth. I don't know why we're using Earth as our lens here, but it makes the same point. And so to the right side, these definitely form an angle. They're not parallel. But you see as this angle, as this object gets further and further, or you look at different objects, then the angle gets smaller and smaller until when we're talking about something very, very distant like the sun or a galaxy or a star, anything really we look at in astronomy, the distance is so great that the angle between one side and the other side is essentially zero. And the light rays really do come in parallel. So that's why we can draw it as such. And when you have parallel light rays, again, a lens will bend them to a focus. So another example, I can do this online. If we go to this refracting telescope, see we here have a primary lens. We have a second lens back here where the eyepiece is. A third lens that isn't in this diagram is if you had a camera. You would have your camera at a lens somewhere, or if you're looking at this through your eye itself is a lens. So there's a third lens not depicted. And so if we open this to light, we let light in, light's coming in, again, parallel from this side. It gets bent by the light. It reaches a focal point somewhere here, and in this diagram it comes out in the second lens. We could call this a collimator. Makes the light parallel, which means when you have your third lens, your eye or the camera, it again brings the light to a focus. And so the purpose of this telescope is to take this big area of light and take all the light and condense it to some place where it can be brought to a very tiny point here. So again, you can see a bright image of a faint object. That doesn't respond that way. So if we go back here, that was a refracting telescope. Again, the first person to use refracting telescopes for astronomy was the great Italian scientist Galileo Galilei. He didn't invent the telescope, but he had heard of a design from somewhere in Holland, and he sort of manufactured his own. And in addition, instead of using it to see ships, which is what they were used for at the time, he pointed it at the sky and looked at what he could see in the night sky. And he saw some fantastic things. He discovered the 4 of Jupiter's moons that you would be able to see through our telescope on top of Campbell Hall. He discovered sunspots on the sun. He discovered that Venus goes through phases. All of these magnificent things that we're going to talk about, and that actually changed the course of Western thought. There's a big reason that we think about things scientifically instead of other ways, and we'll get into that later, Alex will. But Galileo really did the first important work with a telescope. So here's an image of a couple of the telescopes that Galileo used. Clearly these days we have very precise ways of machining the telescopes we want. Galileo was more of a handyman. He didn't do it with nearly as much precision. And so even though by modern standards Galileo's telescopes were pretty junky, they did the trick. They contributed to some really fascinating, groundbreaking discoveries in astronomy. Another person who built a refracting telescope, one that's more relevant to you and me in the University of California, was this magnificent bearded guy, James Lick. And I don't remember how Lick earned his fortune. He was basically a tycoon of some sorts in the 1800s. He was really rich, and he decided that when he died, he wanted to have a pyramid erected as his memorial. I guess that's fantastic. But fortunately, instead of having the James Lick Pyramid, he got some astronomers to talk to him, and they talked him out of building a pyramid for himself, and they talked him instead into building an observatory, the James Lick Observatory in his memorial. Again, he wasn't quite on top of things. He wanted to put it in the middle of downtown San Francisco. And I don't know what the light pollution was like in San Francisco in the 1800s. Maybe it wasn't bad, but having lived here a while, I've noticed that in San Francisco, it's foggy a hell of a lot of the time. I would put downtown San Francisco on like the top 10 worst places in the world to build an observatory. So fortunately, he had these astronomers. They talked him out of building his observatory in downtown San Francisco. Instead, he put it up in the mountains near San Jose, on top of Mount Hamilton to be specific. And that today is the site of Lick Observatory, which is owned by the University of California. And astronomers such as Alex and me and other people at all of the UC schools get to use the modern telescopes at J.P. Lick Observatory. It was founded in 1888. One of the first telescopes that was built there was James Lick's refracting telescope. And so this is a larger refracting telescope. The first lens would be up here. There'd be a second lens here. You can see this is a blurry person standing beneath the eyepiece. Reflecting telescopes, because the light needs to travel in one direction only, you can't really fold the light. It means that they're very cumbersome, long things. But here's a picture of the Lick refractor. And so James did get the last laugh, though. He was not, he still got one thing his way. This is James again. And that is that he had himself buried underneath the refracting telescope. And so if you go visit Lick Observatory, there'll be opportunities to visit. There'll be an essay contest, maybe a field trip up to the observatory later this semester. You can go to the observatory, you can go to the refracting telescope, and you can see where lies the body of James Lick. And actually, there's a little bit of folklore surrounding this. If you talk to astronomers who have spent many, many nights up late at the observatory, they'll tell you that sometimes the ghost of James Lick does go stalking around the observatory. And I don't know, hopefully you guys get to know Alex. I maybe know him a little bit better than you do. Alex Filipenko is a very brave man. And I say this because one night Alex went sneaking around. He went to the site of James Lick's body, to the refractive telescope at night, and he actually got a photograph of the ghost of James Lick. It's creepy, huh? So hopefully if you two go to Lick Observatory, you will see someone who looks like this stalking the grounds. But getting back to serious stuff, there's a reason that refracting telescopes are sort of a thing of the past, and that actually these days most of the telescopes we build aren't refracting telescopes but are a different design. And that has to do with one of the things that happens when you shine light through a lens. And I said earlier that a lens is like a prism in that light, it bends light that goes through it. It's also like a prism in that it bends different wavelengths of light at different angles. And for a prism, that's great because you want to see the different colors of the rainbow. You want to see the light spread out. But for a lens, it's exactly the opposite of what you want. And the reason is if you see, here's an illustration. Light comes through the lens. At first, it's white light. It contains all the colors. Then when it goes through the lens, the violet light bends the most sharply. The lowest wavelength, I should say, bends the most sharply. And so it bends to a point here. The green light and then the red light and all the other colors bend at different angles. And so instead of getting one focus point, you get a whole bunch of focus points for the different colors. And that's really bad. If you try to look at an image that it doesn't have one focus point but many, you're going to get a distorted, blurry image. And the phenomenon that we refer to this as is chromatic aberration. Chromatic aberration is really the downfall of refracting telescopes. One thing you can do to fix it is you can make a lot of different layers of lenses that are slightly differently shaped and try to force all the different colors of light to come to a single focal point. But when you start dealing with big lenses and big pieces of glass, that gets really cumbersome. And so instead, astronomers have a different solution. These days, they avoid refracting telescopes altogether, and instead they use mirrors. They use reflecting telescopes, which has reflections of the light to a focal point. So reflecting mirrors don't have chromatic aberrations. All colors of light bounce off a mirror at the same angle. There's a different thing you have to worry about when you're using a mirror in a reflecting telescope, and that's depending on the shape of the mirror, you may or you may not get a good image. So a simple way to make a mirror is to have it be spherically shaped, to have this curve imitate the curve of a sphere. And the problem is then you get something called spherical aberration, where light that hits the center of your mirror versus light that hits the middle and light that hits the outside, those light all do also go to different focal points. And so if you have the wrong shaped mirror, a spherical mirror, you're going to get spherical aberration. And again, you'll get a different focus from the light that hits the edge from the light that hits the center. And so this is called spherical aberration. Again, it gives you distortions. What you want to do instead is simply design your mirror with a shape that doesn't do that. And the right shape happens to be a paraboloid or a hyperboloid. And so this is a very slightly different shape. You don't really have to notice the difference as it appears. But if you were designing a mirror, you would know that there's a different formula to design a shape of mirror that does bring all the light to a single focus. And therefore, we've gotten rid of all our instrument-based aberrations, and we can get the sharpest image possible. So most telescopes these days are hyperbolic or parabolic reflecting telescopes. The one on the roof of Campbell Hall is, for instance, a parabolic reflecting telescope. Are there any questions on these different aberrations, or on refracting versus reflecting telescopes? None. All right. I think we have another applet to show. I'll get back to this. So here's one design of a reflecting telescope now. So now that we have a reflector, we have one mirror, and you see that there's also going to be a second mirror. It would be all right. You could, with a parabolic mirror, as the one diagram show, have the focus point be out here in front of the mirror, but that can be cumbersome because if you want to put an instrument here to collect the light, and it's a bulky instrument, what you're going to end up with is the instrument blocking the path of the light that wants to come in. And that's no good. So what astronomers usually like to do is we like to have our instrument back here behind where the telescope is pointing. And so what we need is we need one mirror to focus the light, and then we need a second mirror to bounce the light back through the first mirror and to get into here. So I'll show some pictures, but again, if you open it up, you have the light again comes from the left. It bounces off of this parabolic or hyperbolic mirror that focuses it. And so as it's coming together, it bounces off the secondary mirror, comes to focus somewhere back here behind the primary, and then again, there's a lens and another lens for your camera, your eyepiece, to get it where you want exactly for your image. So this is what I wanted. So here are a couple designs. You don't need to remember these terms. One's a Cassegrain design. The other, Newtonian, was invented by Isaac Newton. And again, these are just ways to bounce the light around to where exactly you want it. So here, the Cassegrain design, the one that's actually used most, the light first hits one mirror, bounces off a second mirror, and then comes back to where you put your instruments behind the telescope. All right, so here's a picture of the current best telescope that we have at Lick Observatory. It's much more recent than the refractor that Lick built and was buried under. And this is the 3-meter reflecting telescope at Lick Observatory. This is actually the telescope that to date I have used to do all of my own research. And so it's a 3-meter telescope, which means that this primary mirror is 3 meters across. And so again, as light would come into this telescope, it would come in this way. It would hit the 3-meter primary mirror, which would bend it towards a secondary mirror, which is right up here. And then it would come back down through a hole in the middle of the primary, and you'd have your camera and your instrument set up somewhere here to take the light and process it. Again, just like the picture of the Hale telescope at Palomar that I showed, this dome at Lick is an enormous building. This telescope itself is an enormous structure. This is a huge horseshoe. This is a huge horseshoe-shaped truss that moves the telescope around to point it to different parts of the sky. And again, if you are able to take a tour or go up with Alex to Lick Observatory, you'll actually get to be inside this room and absolutely feel dwarfed by it. It's truly gigantic. Alex will talk to you guys next week about an essay contest there is to actually earn a research trip up there to be with Alex, where he takes a night's worth of data and does some of his research. And I hope some of you guys are enthusiastic about that. I see a question over here at the right. That's a good question. Why don't we need to enclose the area? So you can enclose the area. So part of the reason you don't need to enclose is, first of all, like we said in the diagram I had with the Earth, the light is coming in parallel. So it really is coming in pointed directly from where the telescope is pointed to the mirror. It's not moving off, and it's not like it's going to escape through something that is missing a tube. The other thing is you do want to keep ambient light out, but this large dome that encloses most of the telescope does do most of that. So it's nice, and it's a more lightweight structure if you build it without having a solid tube all the way down. But that's a good question. Are there other questions while I'm paused? Yeah, there's one over here. That's a really good question. So we do have the secondary mirror that blocks some of the light that wants to hit the primary. And how do we compensate for that? And the answer is simply we don't. We let that light hit the secondary mirror and we let it escape. These telescopes are designed that when you have this outer ring that collects most of the light, really the inner area that doesn't collect light because it's blocked by the secondary is pretty negligible. And so it's just a design that we deal with. That's a good question. All right, I'll move on. So that was the 3-meter reflecting telescope at Lick. Here's another reflecting telescope. This one's really cool. Alex's team uses it to automatically detect supernovae. And so this one is smaller in diameter. It's not nearly as large or impressive as the Lick telescope. What's impressive about this one is that it's completely computerized. No one is ever going to manually control this telescope. It has a computer program running that tells it which objects to go to, how long to expose on those objects, and you just let it work by itself, and it collects you data. And it's a wonderful thing for Alex's team. So moving away from Lick Observatory, maybe the most exciting site for telescopes in the entire world is in Hawaii. On the big island of Hawaii, on the dormant volcano Mauna Kea, is the site for basically the world's biggest and best telescopes. And here's a picture of Mauna Kea and all of the telescopes on it. These are the best in the northern hemisphere. In the southern hemisphere, the Andes mountain range in Chile has some really impressive telescopes, such as the VLT. But the Mauna Kea in Hawaii is where it really is at in the northern hemisphere. And so all of these telescopes are affiliated with different institutions, but the granddaddies of them all, the two that we're going to think about the most, and the two that really are the most impressive here, are the twin Keck telescopes on the top of Mauna Kea. And these are the largest optical telescopes in the world, and arguably the best optical telescopes in the world. And it's really a point of pride for us because the University of California gets almost half of the observing time on these Keck telescopes. We split it with Caltech and the University of Hawaii. But astronomers that you see, like Alex, like some of his colleagues, maybe hopefully like me someday, actually do get to use the world's biggest and best telescopes, these Keck scopes. And so here's a picture of one of the Keck domes. Here is the primary mirror of one of the Keck telescopes. You can see there's actually a person standing inside the hole in this mirror. This is absolutely an enormous mirror. It's about 10 meters across, so about a third of a football field from this end of the Keck mirror to the other end. And if you look at this mirror, you can see that it's not actually a single mirror, but it's made up of all of these hexagonal substructures. And so the way the Keck mirror is designed is that a 10-meter single piece of glass would just be way too cumbersome to operate. But instead, we have all of these individual hexagons that combine to make up the Keck primary mirror. So here's some pictures. Here are the sub-mirrors. Here's another picture of one of these hexagons. Each of these are specially curved so that overall this mirror takes on the parabolic shape that we want. So each of these mirrors is specially designed, and they make, again, the biggest and the best telescope you have in the world. This is the T-shirt Alex would have worn had he been at today's lecture. I think my T-shirt fits me a little bit better than Alex's would fit me, but that's what it is. There's a question in front. I believe Keck was the name of a person who had a lot of money, and it's his foundation that built the telescopes. It's going to be really embarrassing if I'm wrong about that, but that's what I think. Huh? Pancho is verifying me. I got that right. Yeah. If you have a lot of money, I encourage you also to try to build the world's largest and best telescopes. Okay, there's a close-up on Alex's T-shirt. And then the last kind of telescope we can talk about, these are also reflectors, are radio telescopes. And so unlike an optical telescope, which collects visible light using glass, you can actually use a metal dish, very much like a satellite dish, to collect radio waves. And because radio waves are much larger than visible light, actually to get a sharp image, you need a much larger telescope to collect radio waves. And so if you think optical telescopes like Keck or like the Lick 3-meter are huge, then these radio telescopes really are huge. So this is an enormous single-dish radio telescope in Owens Valley in California. The largest telescope in the world, the largest single-dish telescope in the world, is a radio telescope in Puerto Rico called Arecibo. And so this is a crater into which has been built an enormous single-dish radio telescope. If any of you guys have seen the James Bond movie GoldenEye, the final action sequence in GoldenEye takes place in and around the surface of this telescope. I don't know how the people at Arecibo permitted that to happen. But, so this is the GoldenEye telescope, and again, it's the biggest single-dish telescope in the world, and it collects radio waves. Another cool thing you can do with radio telescopes is you can build an array of them. And so this is from another movie. If you've seen the movie Contact, the array that Jodie Foster used in Contact was the very large array in New Mexico, depicted here. And so instead of one radio telescope, here we have 27 radio telescopes sort of aligned in a triangular structure. And each of these individually is quite large. For example, these all are on their own railroad car, and in this direction, and this way there are railroad tracks that these telescopes can be moved around to get them in the configuration astronomers want. But we got an even better advantage not by having simply one large radio telescope by many. And that's, again, if we go back to resolution and we think about wanting a big telescope to get a sharp image with good resolution, actually, if you combine the light from an array of radio telescopes, you can get resolution that acts as if, instead of all these many telescopes, you had a single dish that was the overall size of this entire array area taken up by this array of telescopes. So by combining the light in a certain way from these 27 individual dishes, you can simulate a telescope that's as large as the entire area covered itself. And that's a really cool thing that people do with radio telescopes. They're starting to even do it with optical telescopes these days. So are there any questions first on optical and radio telescopes? All right. So all these telescopes I've taken a picture of, I've shown you pictures of, I never took any of these pictures, are on the ground, and they still have to deal with the Earth's atmosphere. Like I said, the Earth's atmosphere blurs light as it comes in from outer space. It also blocks certain kinds of light, like gamma rays, X-rays, ultraviolet light. And also when we're on the ground, we're always dealing with stuff like city lights and other sources of brightness that we'd rather not have to worry about when we're taking images. A solution that astronomers have employed in the last couple decades is simply to take our telescopes, get them off the ground, and move them into outer space. And so hopefully, probably the most famous telescope in the world, one I hope all of you have heard of, the Hubble Space Telescope, is just that. It's a telescope that isn't on the ground, but is orbiting the Earth in outer space. So let's discuss some of the advantages of having a space telescope. The main disadvantage is that these things are extremely expensive. So it would cost the cost of multiple ground-based telescopes to build one space telescope, but they really do have some fantastic advantages. So again, one is you get rid of this atmospheric blurring. Here's the picture of the star again. That's getting, the light of it is getting thrown around, and so this would be a big blur. In outer space, there's no atmosphere to do that. You would actually see a sharp image of a star. Again, we have city lights. I'm not sure if this was taken from Lick Observatory, but if you're at Lick Observatory, you can definitely see the lights of San Jose, and so that is polluting the night sky that you would like to be observing from. Clearly, if you've been to a star party or tried to look at the night sky from here, you know that the Berkeley lights and the San Francisco lights and the Oakland lights give you this haze that doesn't really allow you to see things terribly faint in the night sky. So that's something that we want to avoid by going into outer space. And the third thing is, maybe the most important, you can't even get all the different kind of lights from the ground, kinds of light. And so, for instance, we know that the night sky is transparent to visible light. You know that you can see things. So here is optical light reaching all the way from outer space and making it to the ground. Radio also makes it all the way to the ground. But all of these other bands don't do it. And so going from right to left, you have infrared radiation. Infrared can get through a good part of the atmosphere. But eventually, about 2 to 10 kilometers from the ground, it hits water vapor. And this water vapor absorbs the infrared radiation, and all of a sudden, you can't see it anymore. Another disadvantage to doing infrared telescope astronomy from the ground is that the sky itself is bright in the infrared. We talked about on Friday how based on our body temperatures, we all glow at infrared wavelengths. Well, the sky's temperature in Kelvin is pretty much very close to our body temperature in Kelvin. And so the Earth and the sky also glow at infrared wavelengths. And so it's clearly really annoying trying to do infrared astronomy when you have the sky surrounding you that's glowing in exactly the band that you want to detect things in outer space from. So having a telescope up here above where most of the sky glows in infrared, or even in outer space, is an advantage that gets rid of that glow and also prevents you from being absorbed by water vapor. UV, we know what chemical absorbs UV. Ozone. It protects us from the sun's harmful rays, but it also prevents us from seeing UV radiation from outer space. So if you want to observe UV light, you need to get above the ozone layer. And then gamma rays and X-rays basically interfere with a whole bunch of atoms and molecules, and by the time that they would reach the ground, they will have all been destroyed. That should make sense to you guys if you think back to Alex's lecture on Wednesday, how we talked about how atoms have different energy levels, and if you have a photon of a sufficiently high energy to give it a kick, you'll ionize something and you'll kick it all the way out. These gamma rays and these X-rays have very high energies. And so basically anything that they hit as they're approaching the ground, they're going to ionize and they're going to be absorbed. And so they will never make it to the ground. You'll also have to go into outer space to see these X-rays or gamma rays. So again, the advantage of having a telescope in space is that you get rid of atmospheric blurring, your sky is darker, you don't have to worry about city lights, and all these layers of atmosphere that interfere with different types of radiation at different heights they're not there in outer space, so you can see anything you want. So other things you can do, so here's some solutions to various kinds of light you'd want to look at. Putting a telescope in space is a solution to all of these. For some things like IR or UV or X-rays or gamma rays where you only have to get above a certain layer of the atmosphere, sometimes you can do the trick by sending a telescope up in a balloon or in an aircraft and taking pictures from there. So there's all sorts of ways to get above the atmosphere. The most expensive and the most maybe well-known to astronomers instruments, however, are these space telescopes. And so here's a picture of a gamma ray telescope in outer space. This is the Swift gamma ray telescope. To my eyes, I've probably watched too many shoot-'em-up movies, but this looks like the telescope is actually causing that explosion. It's vice versa. There's some explosion in outer space that is creating lots of gamma rays, and in this depiction, this artist rendering, they are going to the Swift gamma ray telescope. There is the Spitzer infrared telescope. This is where really high-quality infrared observations get taken. This in the background is, I think, a map of the Milky Way galaxy in infrared. So here's an artist rendering of the Spitzer telescope. For X-rays, we have the Chandra X-ray Observatory, another space telescope. And for optical light, we have the very well-known, and this is now not an artist rendering, but an actual photograph of the Hubble Space Telescope, sort of the crown jewel of NASA for the last 10 or 15 years. So here's the picture of the Hubble telescope. It was named after Edwin Hubble, a great British astronomer. We'll learn more about his contributions later. And so here is the primary mirror of the Hubble telescope. It's a 2-meter telescope, so it's not as big as the ones on Mauna Kea in Hawaii, but it's, you can see compared to this people, rather large across. It was certainly a feat to get this thing into outer space, launching it on a rocket. And there was a little bit of controversy caused by this 2-meter mirror, because the first time they set it up in outer space, essentially it didn't work nearly as well as what they wanted to. When we took images initially with the Hubble telescope, instead of getting a nice sharp image of something like a star, we got this rather disgusting, blurred out, odd, distorted, aberrated image of a star. And this has to do with what I was talking about before with spherical aberration in a reflecting telescope. It turns out that the alignment between the primary mirror of Hubble and the secondary mirror was messed up in a way such that something like spherical aberration was happening, and we weren't getting light hitting different parts of the mirror to converge to different focal points, to the same focal point. Instead, they converged to different points rather than what we wanted is them hitting at the same focus. So again, this is something we saw. What we had to do is we had to send astronauts up into outer space to fix the Hubble telescope. They added some additional mirrors that corrected for the aberration. And eventually we got Hubble to get the images that we wanted. So here's a good before-after shot. You can see before, when we had spherical aberration, we had a rather blurry image of this galaxy. Here we have a much sharper image. And so, for instance, if you look at the nucleus of this galaxy, this yellow ball of stars in the center, you can see clearly where the yellow ball is in the after image, whereas in the before image, it's sort of smeared out all over the general center of this galaxy. So again, like I was saying, smaller, finer details are much better when you're trying to get a clear image. And so this is the corrected Hubble telescope. And Hubble has given us basically some of the best, sharpest, most inspiring pictures that anyone on the planet has ever seen of outer space. Here is an example of one of these amazing images taken by the Hubble Space Telescope. This is the so-called Pillars of Creation. And so this is an image of these enormous dust clouds that are in a part of the sky known as the Eagle Nebula. And inside these dust clouds, each of these dust clouds, I should say, is tens to hundreds of light years across. Just completely enormous dust clouds. They would absolutely dwarf the solar system. And inside each of these, you can see these faint points, which I'm not sure are background stars or foreground stars. But like these faint points, inside each of these dust clouds, new stars are forming. That's why they're called the so-called Pillars of Creation, because this is a site where new stars and new solar systems and new planets, and maybe, just maybe, new life is going to form in the universe. And so it's thanks to getting above the Earth's atmosphere, getting images from things like the Hubble Space Telescope, that we can see some truly inspiring, really crystal clear images of where we came from and other things in the astronomical world. Of course, as soon as you get the Hubble Space Telescope, you get the tabloids all over it. So the Weekly World News, which is one of my favorite newspapers personally, reported that they had found an image of heaven photographed by telescope. We found where God lives, says scientist. So you get a little bit of publicity no matter what you try to do. And here's another artist rendering of the Hubble Space Telescope, sort of misleadingly having it as if it's flying towards this galaxy. Hubble simply orbits the Earth, so it's around where we are. So before I get to twinkling of stars, can I take any last questions about telescopes? All right. Okay, so let's get back to twinkling of stars. And so this is an example of what I was talking about before, how the Earth's atmosphere throws around light that's coming through it for outer space and blurs objects. And the way that you see this blurring with your naked eye isn't like the image I showed where the light gets thrown around to different locations, but what you actually see when you look at the night sky, there's a song that I hope everyone knows named after it, is that stars actually twinkle. And this is a result of the Earth's atmosphere refracting and bending the starlight and slightly changing where exactly most of that starlight is going to land. And so a good analogy to the twinkling of stars is if you look at a swimming pool, you see these patterns in the water of sort of bright bands and dark regions. And you know that if you were looking at this in real time, this pattern would be moving all over the place. And so, for instance, if you looked at any one location in this pool, at one instant it might appear bright, and in the next instant it might appear dark. And that's because, again, as light passes through, in this case, the water in the swimming pool, the water is going to bend the light. And because the water in the swimming pool isn't perfectly still, it's moving around. Where exactly it bends most of that light is going to change continuously. And so light that is getting concentrated in one area to create a bright spot, the next instant is getting concentrated somewhere else. And where you were once looking at a bright spot like here, an instant later you'll be looking at a dark spot. And so just like this pattern in a pool, when you see light go through the atmosphere when you're looking at a star, you're seeing a star twinkle in the same way. So here's an image of a star on the bottom and then a planet on top, and I think the tracking has been taken off, whatever took this image, so it's trailing across the sky. And unlike the planet, you can see that as the star is moving through the sky, it's getting brighter like here, and brighter like here and here, and it's getting dimmer. And so if you were looking at this star and just fixing on it so it didn't look like it was moving, you would see it twinkling as it got brighter and then dimmer and then brighter and dimmer. Up here, we have the track of a planet, and as you can see, planets don't actually twinkle very much at all. This is fortunately one good way that you can recognize in the night sky whether you're looking at a star or a planet, is if you look at something and it appears to twinkle, it's probably a star. If you look at a bright object and it's not twinkling at all, then it's probably a planet. And if you look at a bright object and it's coming right at your head, it's either a misguided airplane or a meteorite, and you had better duck. And so here again, here's an example of what you'd see with a star. It's a single point. The atmosphere is throwing it around. And so in a telescope, you'd see it moving around. Even if binoculars, I've looked at stars through binoculars, and they appear to sort of jitter around instead of staying in one place. It's the same phenomenon. But if you just had your naked eye, you'd see it twinkle. A planet, on the other hand, does not twinkle. And the reason a planet doesn't twinkle is that unlike a star, which at its distance appears like a single point of light, a planet is actually a collection of many closely spaced points of light. And so here's a single point that is going to get bent by the atmosphere and thrown around to cause twinkling with a star. For a planet, actually, these many points, since they're all simultaneously being caused to twinkle, and since they're a little bit offset from each other, instead of being thrown around in one single way that causes the planet to twinkle, they tend to average out. And so when you look at a planet high in the night sky, you tend not to see very much twinkling at all. And again, that's because a planet, unlike a star, from our point of view, because they're much closer, appears as a shaped object, a disk, instead of a single point. Because the atmosphere does do some twinkling to planets, as it gets low in the sky and the light has to pass through more atmosphere, you'll start to see planets twinkle, but the effect will still be much less noticeable than a star that twinkles a lot. And so the next time you're looking at the night sky, you should be able to see Jupiter in the early evening after sundown. See if you can pick out Jupiter as the bright object in the night sky that doesn't twinkle, compared to all the stars that are twinkling around it. You'll do much better than your naked eye with an image like this. So here's a picture of Jupiter just to drive home the point that Jupiter definitely has a shape and appears as a disk in your telescope. You can see these stripes in the atmosphere. If you're looking at Jupiter at a star party, see how many stripes you can pick out in Jupiter's atmosphere. You actually can see them on a clear night. And for curiosity's sake, here's one of Jupiter's moons, Europa. You can see it casting a shadow on Jupiter. And so if Alex were here, he would point out that if you were a being floating or standing on this point right here in Jupiter's atmosphere, you'd actually be witnessing a total solar eclipse because you would be in the shadow of the moon, Jupiter. So I say again, I encourage you, go out to the star parties, see Jupiter and its moons. You can see more than just Europa. Here's a nice picture of different planets in the sky. This would be the planet Venus. It's the closest planet to the Earth, and so it appears the brightest. Up here, I think, is Saturn. Actually, I think this one is Mars. I'm going by memory on this. This is Mars, this is Saturn. I think this is a star, Aldebaran, and this is Mercury down here. So if you're lucky enough, you can get a point in the night sky when many of the planets come together. And if you looked at these, you might see Mercury twinkling because it's getting low near the horizon, but these would all appear not to be twinkling at all, and you'd be able to tell them apart from being stars. So we've got 3 minutes left. I can start into the topic of adaptive optics, but first I want to make sure that everyone's on the same page. So again, are there any questions? All right, none. So bear with me for the last 3 minutes. I'll get ahead so Alex will have some less ground to cover. So adaptive optics, we've been talking about how atmosphere makes stars twinkle, and when we're talking about using a telescope, it makes the images blurry. And I said at the beginning of this lecture that at some point, making a bigger and bigger telescope stops being an advantage for resolution because the atmosphere is going to defeat you anyway. Well, guess what? In the last, again, I'm going to say 10 or so years, astronomers have started developing a way that we can get the atmosphere back. We can beat the atmosphere, and it's using this technique called adaptive optics, which actually takes the distortions that the atmosphere performs on light, and those distortions, and it corrects for them. It does the reverse of those distortions, so all of a sudden we're getting clear images again. And once you have something that can correct what the atmosphere does, now as you start building bigger and bigger telescopes like the Lick 3 meter or like the Keck telescope, then all of a sudden that size is an advantage. And at these biggest telescopes, you can actually get better resolution for some things than you can get with the Hubble Space Telescope in outer space. So Hubble used to be by far the best telescope in terms of resolution. Now, I say on a clear night, on top of Mauna Kea with adaptive optics, because the Keck telescope is about 5 times bigger in diameter, about 25 times bigger in area, you can actually beat Hubble with the Keck telescope in Hawaii these days. So I don't even have a minute to describe how adaptive optics works. I'll leave this to Alex, but instead I'll show you guys an animation. This shows what a star looks like with no adaptive optics whatsoever. If you were looking at this, and I think this was taken with the Lick 3-meter telescope, you would see it like this. When you correct for the atmosphere, you see something more like this, and it's actually a movie. So you can see it flying around. It's moving all over the place. It's really big and blurry. You can't really even tell this is a star, can you? No, but once you correct it, you get something nice and compact. It stays in the same place. You can identify that as a star. And Alex is going to tell you how that works on Wednesday. Thanks a lot, everyone.